Alright, so I'm going to start off this week just by reflecting a little bit on what we've learned so far in terms of consistent nodal loads, as well as extending a little bit on the ideas that we've had, just to round off our understanding of consistent nodal loads for two-dimensional elements. Okay, so what I want to make sure is that we just completely understand how consistent nodal loads work over multiple elements, because I've had some questions via email on that, so I just want to make sure that we have a quick discussion on that. But then I want to extend a little bit and say, how do we apply point loads between nodes? And I just want to show you, it's so simple to do, just based on the ideas of understanding what's going on, and then also just want to do body forces. So if you have sort of a body subjected to body forces, how do we actually compute that? And I just want to go back and just remind you that you've got all of that already in place, okay, to be able to do that. So I'm just going to really just apply the maths and the basic ideas. Okay, so first off, you're going to model our first model is just we want to have now uniform, because a uniform distributed load over this mesh. We've got two elements, so if you look at the height here, it's total 4, 8 long, 1 thickness. And so what we can inform is, so what we want to apply is essentially a uniformly distributed load T of 150 newtons per millimeter squared. Okay, so that's what we want to apply on this edge. So in the end, we expect to see 150 MPa. We want to see uniformly distributed 150 MPa load. That's what we know what the answer should be. Okay, this is what this means. We're essentially applying 150 MPa traction on this right hand edge. Okay, so each element has a length of 2 millimeters. So what we can first get out is essentially, if you have 150 newtons per millimeter squared and it's 2 millimeters long, then each edge should have a total force of 300 newtons. So that is a total load per edge. And if we just go for our normal approach of 1/6, 2/3, 1/6, so then 1/6 of 300 would be essentially equal to 50. 2/3 of 300 would be equal to 200. And so that will be a 50 again. So all that we have to do is we have to apply those loads. So let's open up this file and make sure that we've applied that. So I can go for my 1/6, 2/3, 1/6 split that we've already now computed multiple times, but just to show you, this is the 300 because I need to compute the edge length. So take the edge length, take the distributed load and the thickness, and that will give me the total force. And it's uniform. That's why I can split it down this 1/6, 2/3, 1/6 approach. Okay, so let's make sure we open up that file. Q4 to add 600 newtons, so let's open that one. There we go. And essentially 50, 200. The middle node has a 50 contribution from this element. Because this element edge is also 2 millimeters, the total load here is also 300. So 1/6 of this 300 would be also 50, so that's why I get 100. 50, 50 plus 50 is 100 there, and then 200, and again 50. So that's what we see, essentially the loading. So this is the file, the loadings that we've applied. Okay, and just again to confirm, if you run this, everything is nice and as expected. There's a magnification factor, there's a Mises 150 MPa, sigma x 150 MPa, 0 sigma y1, 0 sigma xy. Okay, so that's what we see there. Bob's your uncle. Okay, let's go to the next step and say, okay, let's simplify the problem one step. Let's apply a point load of 1000 newtons in the x direction on any node. So what I'm going to do is, let's apply a point load here at node 37 of 1000 newtons. So when I apply this point load here, it will pull, and there will be an induced moment on this structure because of the fact that this thing is offset from the neutral axis. There will be an induced moment. Okay, so let's apply. Start off by applying this 1000 newtons on the x direction. But what I'm going to show you is a different way to compute where to apply that load. Okay, that's consistent with what we've done. So all I know is node 37 has to get 1000 newtons in x direction. That's what I know. But I just want to show you there's another way we can compute it. And that's really just to take n transpose multiplied by px times comma py. That is really a result of applying tractions when a traction is essentially integrated over a point. Then that would be solved from the traction equation, which would really just translate towards n transpose multiplied by px comma py, where px and py is the x and y directions point loads. Okay, what is important is I need to evaluate n transpose at where I want to apply px and py. So if I'm on this element here, And if I think about just this element for now, I'm just going to highlight this element. I'm going to look at it in the local coordinate system. So this will be node 1, 2, 3, 4, 5, 6, 7, 8 in the local coordinate system, so the local numbering. Then essentially I can set up the n matrix for that, where I have all the odd indexes from 1 to odd, let's not call it odd indexes, but odd positions, like position 1, position 3, position 5, 7. They'll related to the x directions, and all the even ones will be related to the y. That's what we see there. And so all I need to know is in this element in the local coordinate system, which starts here from psi 0 and eta 1, psi positive, eta positive from here onwards. If I want to be at 37, I just need to say psi is equal to 1 and eta is equal to 1. So I just need to make sure I evaluate this n matrix at psi equals to 1 and eta equals to 1. That's all. So that's what I'm doing here. Take the transpose of that matrix and multiply it by my point load, which is 1,000 in the x direction and 0 in the y direction. That's why I put 1,000,0. And if I do that, then what I see is essentially I need to apply 1,000 newtons on, so this is then a node 1 x and y, node 2 x and y, node 3 x and y. So this will be node 1, node 2, node 3 x and y, and the x is 1,000 and the y is 0. So I just need to put 1,000 on node 37. And that's what I have to do. Okay, to be able to apply this loading. The benefit of this approach is this now allows me to actually apply point load anywhere, because I just need to figure out what psi and eta I want to apply, and that we'll see in the next one. But let's first show you the result of this. So I'm going to open up this file. So this is input 1,1. Input point 1 underscore 1, underscore 1, and what I see is a point in the x direction 1,000 newtons on node 37. I've put 28 and 23 in here because we'll see now they might not be 0. Okay, when I start shifting away from a node. And so let's just run this so you can see what the expectations are. So that's that. Here I'm running this 0.11. So let's see what we get out. If I run this notebook, what I see is essentially this kind of deflection here. Beautiful. So that's the moment that's being applied, because I have a sort of a positive moment, negative moment because of the negative curvature. And then essentially I've got von Mises, I've got sigma xx, sigma yy, and I've got some reaction forces that I'm just plotting here. So what I want to look at is what is the reaction forces here. So the reaction forces here is a mixture of a uniformly distributed x, because if I look far away on this right hand edge, it will be sort of a result of a uniformly x plus a moment that will be there. That's why I get sort of this interesting reaction forces. What I want to do is just keep track of these reaction forces if you were to start moving away the node, okay, from a node, and then see that the values sort of progressively make sense and that the responses make sense. So what happens now if I want to apply load halfway between 37 and 28? So halfway between 37 and 28. So I want to do it halfway. We know that essentially here eta is equal to 0. Here eta is equal to 1. So halfway, because it's a nice square and even rectangular element, but it's a nice undistorted element. So that point there would just be halfway. So halfway between that would be at equivalent of an eta equals to 0.5. Okay, so I'm going to apply load here. So between these two nodes, at equals eta equals of 0.5 and its psi equals to 1. So I'm going to apply 1,000 there. So let's do that. What happens if I want to do that? Again, same story. Get my shape functions, put it into the n matrix, and now I'm just evaluating the psi at 1 and eta equals 0.5, and I multiply by my point loads that I'm going to apply 1,000,0. So everything's exactly the same as before. The only difference is I'm substituting an eta of 0.5, and let's run that. And if I run that, then all of a sudden what I see is, this is the consistent nodal loads I have to apply to represent 1,000 newtons being applied between those two nodes. And so what this means is, at node 1, nothing. At the second node in this local coordinate system, so the second node, node 1, node 2, that's the second node in this local coordinate system. That means there I have to apply a minus 125. So remember, minus 125 for 23. Then if I look at that the third, second node. The third node, I need to apply 375, so that's there at the top. I need to apply 375 there, and then essentially what we see later on is 1, 2, 3, 4, 5, 6. So let's see. 1, 2, 3, 4, 5, 6. At 6 I need to apply that other value that you see there, 750. Okay, so that's in the middle at 28, 750. So let's open up the file, the way I do the halfway, and I can see at node 23 minus 125, at 37 at the top, 375 in the middle, 750. And now if I run this one, I will actually get the response that I'm hoping for. So let's go. So let's do this halfway one. So there I'm the half. Let's run it quickly. And what I just want to show you is beautiful, nice result that I get out there. Sigma von Mises, sigma xx, sigma yy. But what I can show you is essentially the reaction forces. And so if I show you now what's going on between these, so do this one's reaction and this one that we used before, that one's reaction. So here we had 166, the top one there, and now it's gone down to 104. There was a 0 in the next one, it's remained the 0 here. This went down from 167 to 41, from a minus 167 to 166. I've got here minus 83 down to a minus 70, minus 333 down to minus 270. Okay, so that's sort of the reaction forces. And just to demonstrate this a bit nicer, what I'm going to do is I'm going to go from node 37 to 28. So I'm going to go in increments of eta of 0.2. So I'm going to go from 37 to 28 by going from at eta equals to 1, then 0.8, 0.6, 0.4, 0.2, and then 0. Then I'll be here at 28 itself. And I just want to show you sort of the responses that we get. If I do that, this is the one that we've computed already. That's for the 1, so that's at the top. Then eta of 0.8, we get this these values here. So we're going down from 166 to 141, still 0, 167 here, 167 here goes down to 116 and 167 there. Then essentially I've got this minus 83 going down to minus 78, minus 333 down to minus 308. Okay, and we know that this one is just at a node, nothing funny. This is the one that's off a node. Okay, now I'm going down to 0.6, and if you do that, you start seeing a nice gradual still change in these values. This 141 down to 116, still 0 there, 667, that remains sort of close to 167, minus 78, minus 373, minus 300, so minus, whatever I say, 78, minus 783, minus 733, minus 308 down to minus 283. Okay, and I can go down like this just to show you as these values change consistently. This is now down to psi of 0.4, at psi of 0.2, and then at psi of 0. So this is now at node 28, and you can see essentially how things are going from minus 90, from 91 to 66 down to 41. Still have a 0 there, 167 minus 167, so this is 166, wait a minute, yeah, so 166 down to minus 33 down to minus 83. Then I've got here minus 166 down to minus 166, there again, minus 166, very similar, minus 68 down to minus 63, down to minus 58, and then lastly, minus, I'm sorry, I'm saying 68, but 680, minus 280, 258, minus 233, down to minus 208. Okay, you can see nicely that. And you're welcome to go and confirm that indeed, if I were to apply the loading like this, so if I were to apply the loading like this, let's go here, for instance, that essentially what I induce on this side's reaction forces would be sort of a moment, and the moment would be given by the arm, so this force times the arm, plus then a uniformly distributed load that we get out of 1,000. So that will be sort of the superposition of those two things should be resulting to that reaction force. Okay, so this is just to show you more or less how things nicely consistently change. So you can see here everything is changing quite nice and consistently as we progress along. Okay, so that hopefully puts this to bed. Just take note, this is minus 308, so the 2 minus 783 minus 167 minus 1717 minus, so that's plus 141. Okay, so I might have said something here as 1678. My apologies, just double check there. That stands for 100. Okay, so it's just a little bit in my not focusing. Okay, 100%. So that's just to make sure that we're all on the same page.